class. I welcome you to our chemistry lesson today. Today we are going to look at the large-scale manufacture of ammonia. The process is known as the Haber process. And our discussion will start from the raw materials, and then later we will look at the uses of ammonia. That will actually be a justification as to the importance of producing this compound in large scale. So the uses will come towards the end, but first we'll consider which materials are being used, and then move into the actual process, the actual Haber process. So I just want you to know that the Haber process is actually the term, or it's the term used for the large-scale manufacture of ammonia. The raw materials, one is nitrogen and the other one is hydrogen. Actually, ammonia is a compound that comprises of nitrogen and hydrogen in the ratio 1 to 3, and we shall see that in a short way. The sources of nitrogen mostly is obtained through the fractional distillation of liquid air. That is the main and the major source of nitrogen. The main source of or sources of hydrogen will include from natural gas or as a byproduct of cracking long-chain alkanes. And for any industrial process, it is important to actually identify the sources of the raw materials, how to obtain them. Now, in the process of the manufacture of this ammonia, the Haber process, nitrogen and hydrogen are mixed in the ratio 1 to 3. It means for every 1 for nitrogen or 1 mole of nitrogen, you require 3 moles of hydrogen. For every 1 of nitrogen, 3 of hydrogen is required. When these two are mixed together in the ratio 1 to 3, the mixture is then passed through a purifier, and a purifier actually removes impurities. These impurities are removed because they are known to poison the catalyst. To poison the catalyst is simply to reduce the efficiency of the catalyst, and therefore it's important to purify or to pass this mixture through a purifier to remove the impurities. And some of the impurities which are being removed actually comprise of the dust particles. You also have carbon dioxide and also sulfur dioxide as some of the impurities being removed in this process. The mixture of nitrogen and hydrogen, that is in the ratio 1 to 3, is then passed through a compressor. The compression is between 200 to about 500 atmospheres. We talk about atmospheric pressure. Then, once it has been compressed to that very high pressure or pressures, then it is passed through a heat exchanger where you have temperatures ranging between 400 and 500 degrees Celsius. Thereafter, the mixture is then again passed through a catalytic chamber where you have a catalyst, and in this case, the catalyst which is used is actually the ion catalyst. So the conditions which have been indicated here are actually what we refer to as optimum conditions of temperature, the presence of a catalyst, and also you have the pressure being indicated there. Now, once this has been done, then nitrogen will combine with hydrogen, like indicated in this equation, to produce ammonia gas, and the reaction is highly exothermic. It produces a lot of heat, and we'll also see later how important this exothermic reaction will be in terms of making the process to be more economical and subsequently to be efficient. Now, the unreacted, worth noting is the fact that not all nitrogen and hydrogen will actually react. Some will not react, will remain unreacted, and therefore, for the unreacted gases, it is passed, or these gases are passed into the heat exchanger again, such like you recycle them back through the heat exchanger. therefore making the process economical. So it actually minimizes on wastage, because any gas which is reacted is also taken back, and the process of taking the back actually reduces and minimizes on wastage. The ammonia produced then is liquefied in the condenser, and it is stored in cylinders and ready for distribution to the consumers. The unreacted gases are recycled, therefore reducing wastage as indicated. You look at the flow diagram here for the Haber process, and it simply actually makes a summary of what we just mentioned, that you will have nitrogen and hydrogen from their various sources, fractional distillation of liquid air from natural gas or cracking of long chain alkanes, and then into the purifier. This is where impurities such as dust particles, carbon dioxide, sulfur dioxide are removed, and the importance of removing the impurities is simply to prevent the catalyst from being poisoned. Then now, nitrogen and hydrogen into this compressor, where there is going to be compression of between 200 and 500 atmospheres. Then the mixture of the two gases under very high pressure into the heat exchanger, where here you have the heat exchanger producing temperatures of between 400 and 500 degrees Celsius. Once again, the hot mixture of nitrogen and hydrogen under very high pressure, then into the catalytic chamber, where you have the ion catalyst. This is now where the actual reaction takes place, where this equation now, or rather this is where you have the reaction, nitrogen, hydrogen, to produce ammonia gas there. And we can clearly see that from the catalytic chamber back into the heat exchanger, you have 10% of ammonia being produced, and the unreacted nitrogen and hydrogen is also taken back into this heat exchanger for now the continuous reaction of the two gases to actually minimize wastage. 10% is too low. If you were to allow these gases to just be released, then the process will actually be not economical. It will be too expensive because you only produce 10%. But the fact that you're recycling them back makes the process to be efficient. So the unreacted gases will again pass through the catalytic chamber and again. But now the ammonia which is produced now, it's actually ammonia gas which passes through this into the condenser, where it is condensed, then it is liquefied, and it is actually stored in cylinders ready for distribution. Now, if you have also other unreacted gases, then you also have from the condenser back to the compressor, and the whole process again continues until we maximize on all the raw materials which are being produced. That simply also is a summary of the Haber process. And to reduce these production costs, the following optimum conditions must be met. Now, we have temperatures of about 500 degrees Celsius, pressure of at least of around 200 atmospheres, and finally the catalyst which is required is the ion catalyst. So these are the optimal conditions which will actually reduce the production costs and make the process to be very efficient and also economical. Some of the uses of ammonia now, one of them, it is used as a fertilizer. Ammonia is actually used as a fertilizer. It is used in softening water. It is used in the removal of greasy stains. Used in the manufacture of hydrazine, which is actually rocket fuel. Used as a refrigerant, especially in large scale, as a refrigerant in ships and also in warehouses. And finally, it is used in the manufacture of nitrogenous fertilizers. Looking at these very many and important uses, it now justifies the need for the production of this ammonia through the Haber process. That marks the end of our discussion.